I think this was originally going to be an introduction to Bayesian statistics, but I decided to focus on testing because a lot of people at Flatiron have come to my office and said, hey, I'm fitting a Bayesian model. How do I know if it works? So let's take some first steps toward answering that question. So this is the textbook form of Bayesian workflow. This is just, workflow is just what we mean by the process we use to fit models, test models, everything else. It just encapsulates pretty much everything you would do, right? And this is taken out of Andrew Gelman's Bayesian data analysis textbook. It's literally the very first page of the book, right? And this is what you're supposed to do. You set up a full probability model, right, taking into account everything you know about the known values and the unknown values, that is things that you can observe, things that you can't observe, consistent with what you know about science in the world, right? And then we gather some data. We're doing empirical science here, and we condition on that observed data for our model and try to draw some conclusions. We get some kind of posterior distribution over quantities of interest. And then steps 3 and 4 here are actually novel for statisticians. In fact, I think you would get the majority of the statisticians in the world would slap your wrist if you tried to do 3 and 4 and stood up in front of a room of people and said, this is what I'm going to do, right? What we're doing is kind of a pragmatic Bayesian stuff that's going to be close to frequentist stats in the way that I'm going to tell you that we calibrate it. But it's also going to be close to machine learning or engineering, in that we're seeing the goal as trying to make a good model of the world, not trying to do a hypothesis test that we've set up ahead of time, right? So what we want to do once we fit a model and seen what the implications are of that model, we want to say, does it fit the data? Are the conclusions reasonable? Is it sensitive to the assumptions? And part 3 is mainly what I'm going to focus on in this talk today. And then the idea is if that fails, you iterate, go back to the beginning and do it again, right? Obviously, if you've done something like pre-registered your approach, you're not going to be able to do something like this. You're going to be locked into doing one thing that you pre-registered, right? So I'd say there's some drawbacks to doing things like pre-registration. We're going to do this much more like machine learning because we're not trying to do a hypothesis test. We're not going to pollute our inferences from this. The ultimate test of our models are going to be what happens when we apply to held out data. We've got some data. We're going to see new data in the future, right? Really what we care about is, are we getting that right? Right? So Bayesian workflow involves a whole bunch of things, and I'm just going to enumerate some of them here, right? So it starts from designing experiments and collecting data. Often in computer science, we're just given our data and statistics. Somebody had to think about what data to collect, right? You can do a lot of statistics, and I would urge you to get statisticians involved before you've collected the data to help design the experiments. Right? Then you need to come up with some kind of probability model if you're going to be doing statistics. We need to be able to evaluate the likelihoods and priors that we have. We're going to have to do some computation there. We're going to have to figure out how to take the model that we have and fit it to the data. We're going to have to validate our computation, which I'm also going to talk about today. We're going to have to address computational issues that come up, which is a pit you can fall down and never come out of. I'm not going to address that a lot today. And then we want to evaluate and compare model fit and predictions. And then we want to modify and improve the models. And often, we want to deploy these models in practice. That is, we're working at a company. We're working at a public health institution. We're going to do something with our models. We're going to predict what COVID looks like next week and decide what lockdown policies we're going to do. Right? We're going to decide where to play our second baseman in the World Series, right, for a more lighthearted example. Right? And the point I want to make in this talk is it doesn't really matter how you get these inferences. I'm assuming that somehow you somewhere have gone out and gotten some inferences for this, right? We can do that with Markov chain Monte Carlo, which is mainly what I work on. You can use sequential Monte Carlo, which is another Monte Carlo method. You can use variational inference, which almost all the ways you formulate it can be thought of as a Monte Carlo method once you fit it, right? Or we can use variational inference methods. Variational inference when we're using richer neural network type models like normalizing flows or diffusions, right? A variational inference shows up in 2 places because depending on how you do it, it tends to show up in different literatures. Simulation-based inference, where we want to emulate a likelihood or some other part of the dynamics of our problem with a neural network. Maybe we've got a giant pile of PDEs for gravitational lensing, right? We've got some observations. It might be easier to simulate that system forward and train a neural network to actually evaluate those densities than trying to differentiate through your giant system of PDEs. Things like amortized inference, that's becoming very popular, where you set up a neural network to map from your data to your parameters. The last one's the one that doesn't quite fit into this paradigm, because often in something like amortized inference, you don't have a way of drawing samples. You don't have a natural way of representing uncertainty there, right? So you have to model that all separately. This I just wanted to show you. So this is from our paper from 2020 on Bayesian workflow that has like 15 authors on it. You're not meant to read this. You're just supposed to understand that below all of those things I said is another layer of recursion. And then, like everybody else has said today, you could take any one of these boxes and sort of make a career out of it, right? We're not going to do that. We're going to stick to the high level, right? So first thing I'm going to do is set some notation and tell you essentially what we're doing with Bayesian models. And again, this doesn't really matter how you fit them. This is just setting up the ideal sort of normative thing that you want to do. Right? So I'm going to let Y represent observed data that we're going to model. There might be some other data that we observe, like covariates and other predictors and constants and things that we're just going to sweep under the rug. Right? Y is going to be something we're actually going to model statistically. Theta are our unknown parameters. These are the things we want to do inference about. And I'm going to give you a short example of this soon. Right? Then, just to set up notation, we're going to have a prior distribution, which is expressed as a distribution over the parameters. It's what do I know about these parameter values before I start. A sampling distribution that says, hey, once I've got my parameters theta, how do I actually observe my data? This is what people would call a generative model in machine learning. Right? We can think of a likelihood function. Technically, the likelihood function is a function of the parameters for fixed y. The likelihood function is not a probability distribution. It's not a probability density. Sampling distribution is a density or a mass function or something mixed. Then we can talk about the joint distribution, which we know from just the law, the chain rule, that that's just the product of the sampling distribution times the prior distribution, and that gives us the distribution of how those two things go together. And then what we're really interested in for inference is what we call the posterior distribution. This is going to be the distribution of our theta items given our data. What are we going to learn about our parameters from having seen the data? And what I've written out here is just Bayes' rule, which very cleverly converts the probability of parameters given data into an expression that only involves the sampling distribution in the prior, right? So this is sometimes called Bayesian inversion, and that we're interested in theta given y, and we've re-expressed it in terms of y given theta. And this is proportional if we forget the thing on the bottom, right? That's just a constant based on the data. Right? We just get something proportional to the sampling distribution times the prior. Right? I should have said, feel free to interrupt me with questions as we go along. If things aren't clear, I'm kind of going to build on this, or at least take this notation going forward. Right? This is probably way too fast to actually learn Bayesian stats if you haven't seen it, which is right. So one important point, right? The prior and the likelihood can only really be understood together. They don't make sense as independent items themselves. You can't talk about what's my prior distribution for parameters unless I know what likelihood or sampling distribution they're going to be used with, right? People agonize over the prior. Somehow people over the last 20 or 30 years have been taught that using a prior is putting your thumb on the scale, that it's like, oh my, I'm going to be very subjective setting this prior. I'm a scientist. I don't want to be subjective. Well, guess what? You chose the likelihood function. The likelihood function has a much bigger impact on all the inferences that you do, and choosing it is equally subjective. Some deity doesn't come down and say, this is the right likelihood function. We just pull something out convenient. We do a logistic regression, not because we really believe responses are linear on the log odds scale, but just because it's convenient to compute with, it's close enough. Right? You can agonize about that decision as much, in fact, you should more than you agonize about the prior. right? Often in applied work, we don't have a very strong prior that incorporates lots that we know about the problem. Sometimes we do. Like if we're doing a pharmacology problem and we're looking at the 5th generation of a drug, we've had 4 generations before, we might know a whole lot about how that drug operates on the body and how the body clears the drugs. Then we can throw down some very informative priors. But typically, at least in the kind of practical Bayesian work I do, we're just using the priors to determine the scale, right? We're using something called a weakly informative prior that doesn't give you a lot of information, but it says, hey, we're trying to estimate human height. Maybe it should be on the order of a couple meters, not on the order of 20 meters or millimeters, right? That's not like adding a whole bunch of information to that problem. And it turns out this can really help computation. It can really smooth out the computation, adding just a little bit of prior information. And then the sampling distribution encodes a data generating process, which is typically a scientific forward model coupled with a noisy observation model. And now I'm going to give you an example of that, which I think is a really fun example. I think I actually stole this from Charles, who I think you guys actually went and did this, right? And had people drop balls and do things with cell phones and whatnot. But
we did a workshop on Stan at MIT, and then we asked them to come up with an experiment of their choice to measure the gravitational constant.
Yeah, we did this experiment in high school, and I got in trouble because I faked the data. But I'm like, I don't want to roll a bunch of balls down. I have the equation here for what the answer is. And my physics teacher said, no, you didn't measure this. This is way too close. He was on to us. So. But anyway, this is Galileo's experiment for measuring the gravitational constant. At least we can use it to do that, right? We start with a ramp. We roll a ball down the ramp, and we measure the position the ball's at versus time after we release it. Right? Basically, what we're going to do is we're going to solve Newton's differential equation for the expected position, given the initial position, the slope of the ramp, in an unknown gravitational constant. Right? We're going to set this model up so we can actually infer what the gravitational constant is from data. Right? That's the point of doing this. That's our goal, is to learn about the gravitational constant. Right? And we know the measurement position. Right? We're going to express our prior distribution as some kind of distribution over plausible values of this constant. It depends what scale and units you use. That's just completely made up. I have a better one on when I do this for real on the next slide. Then you want to measure the measurement error of your process probabilistically. So the idea is I'm dropping balls and then I'm measuring time, but that's not perfect. I can't measure time exactly. I haven't measured the exact real valued position exactly. So there's noise in my measurement, right? And we want a model of that noise. And then we're going to evaluate the posterior to see what we learned. We've collected some data Y, and we want to figure out what did we learn about the gravitational constant. So let's do it, right? I thought I would stop to just show you a picture of this because it's so cool. This is from the Galileo Museum. This is actually what Galileo's ramp actually looked like. And he had a bunch of little sensors here along the way. So I'm gonna do a simplified version where we only measure the time for it to get to the end. Right, so we're going to simulate some data. Right, so we're going to do this in Python. Right, we're going to have a number of data points, how many times we roll the ball down the ramp. We're going to have a length of the ramp, we're going to have a height of the ramp, and then we're going to have some noise sigma, which represents the noise in our observational process. Right? I'm going to start with gravitational acceleration just to a couple digits here for simulated data. Right? Then we're going to compute this hypotenuse here. And as Alex intuited yesterday when I told him there's this weird 5/7 constant that shows up in the denominator and gets flipped upside and multiplied by 2, it's because we're solving for a solid sphere's moment of inertia here. I didn't actually do this. I had ChatGPT do this. The O1 preview is really, really good, and it explained all of this to me. And I made sure I went and then read some tutorials after GPT explained it to me to make sure it got all the algebra right and matched the actual textbook answers. But I'm not sure I would have understood the textbook answers beforehand, before getting the answer from GPT. So like it wrote this code, right? I formatted it so it would all fit here, right? And we're going to take log normal observation. So a log normal distribution just means the variable is normal on the log scale, right? What this does is it leads to multiplicative errors where the error you make in measuring time is proportional rather than additive. I'm not sure this is a good model for noise, but it keeps everything positive, right? Which is good because we're not going to be measuring negative times, for instance, right? So we have some prediction t. So that t is what gravity theory and inertia and spinning balls and all of this says is going to happen under like a frictionless setting. And then we're going to get our observations, which are drawn randomly around that expected time with a log normal distribution. And then we're just going to return the data. And since we really believe in the stuff that Jeff was talking about earlier, we've encapsulated this as a little function called simulation. So we can just write this down here and do it again for a bunch of different trials. So this is going to give us our data, right? So we're going to run this. We're going to get 100 observations of what might have happened for somebody rolling a ball down a ramp. Right? Now, this is the only time I'm going to talk about STAN. STAN's the project I worked on most of the time. It's a probabilistic programming language that lets you define statistical models. And the way it does it is you declare data. So that's going to be the length and the height of the ramp, the number of times you rolled the ball, and the time you measured for each ball rolling. That's just the data coming in. We're going to actually compute this S value based on the length and height, so we only have to compute it once. Right? And then we have two parameters, two unknowns here. One's the gravitational constant, and one's our measurement error scale. We don't know either of those before we start. Then the model, I'm just going to have some weakly informative priors that says we don't expect sigma to be in the hundreds. We don't expect it to be 0.001. We expect G to be somewhere around log 10. Right? We know it's 9.8, but that's a very broad prior there because it's multiplicative. We're going to calculate what the true value is, right, on the log scale, and then we're going to do the observation. Right? We're just going to say the observations are log normally distributed around the log of the true value. So this was just if you go back here, there's the true value t, and then we just computed on the log scale by taking a log, which is more arithmetically stable, fits in with the log normal distribution. So that model represents this experiment, right? This is the probability model we're assuming, right? And we've assumed a scientific model of how this ball is going to roll down the thing, right? This is our forward scientific model that says we can predict this. In general, this might be some kind of dynamics model. Like if we're doing population dynamics, it might be Lotka-Volterra. If we're predicting the election, it might be a big linear model on the log odds scale and so forth. Right? The forward models look very different. This is just like the simplest possible sort of useful case for Bayesian statistics. Now we just import the command stan pi package, we calculate a bunch of Monte Carlo draws, and then we do the summary. Right? So what this is going to do is going to give us our posterior estimate of G, which it's saying is 9.8. And then it's going to give us uncertainty intervals. It's going to give us both a standard deviation, but it's also saying our data is consistent with that being anywhere between 9.5 and 10. Right? That is, we're 90% sure that the value is in that range given our 100 observations. If we'd done 10,000 observations, that range would be narrower. Right? The more data we collect, the less certainty, we get rid of more uncertainty. The fit diagnostics are good for this. We actually recover the parameters. You see that sigma simulated was 0.1, and this is very close. And the estimates are actually going to converge as we get more data. So this is just how you do Bayesian statistics.
Can you just remind us what the data, if you plotted the data, it would look like values of t, it would be like a scatter plot with like it's...
It would probably be a histogram. Like we'd draw a histogram of the plot of the t's, and they'd be log normally distributed around the expected time. So we'd see a log normal distribution with a location equal to the log time that's actually expected.
Okay, but you're running different s's? Like you're trying different slopes of ramp and things?
You could, but all I've done is I've fixed one ramp.
You fixed one ramp.
Right. There's going to be a length,
Okay, so
a length that we run and a height we start at. Yeah, we could vary that, obviously. We could make these things arrays. Each ball roll could have multiple observations, or it could have its own length and time.
There's no variant, whatever you call it.
Not in this simple model. We've just fixed the ramp up. We measure from beginning to end, and that's it. That's it. We could do all those things. In fact, if I was doing a class, that would be a logical exercise. Take this STAN program, modify it to do that. Right, so we get reasonable estimates. So what makes this inference Bayesian, right? Well, normally people, at least in machine learning, will call any method Bayesian if it involves a prior. right? It turns out the prior is not the important part of making something Bayesian. A statistician doesn't call something Bayesian unless the estimates it gives you are averaging over posterior uncertainty in some way, right? What Bayesian statistics do is really about taking your uncertainty into account, right? So it involves posterior expectations, typically defined as posterior averages. And let's go through some of those. Let's say we want to estimate a parameter. So what I gave you here, these are parameter estimates, 9.8 and 0.089. That's my best guess as to what those parameter values are after I ran this. Right? So the way we do that is a posterior expectation. If I've got some random variable theta, right, and I'm trying to figure out what happens to it after I observe y, then I have this conditional expectation, which is just a posterior average. So everything in Bayes looks like this. It looks like, I mean, not everything, but almost all the inferences we do look like this. They look like the expectation of some function of the parameters. Here's just the identity function, which means we're just going to do an integral over our posterior. So what we're doing here, this integral is just averaging over our posterior uncertainty. Right? P of theta given y is our posterior. That represents our uncertainty in theta given the observation. And now we're just going to average values of theta, and we're going to weight them by the posterior. All of Bayesian inference works this way for the most part. Right? This estimate has a really nice property. If your model is correct, that is, you've chosen the correct model, then the posterior expectation minimizes expected square error. This is essentially what Gauss did when he was working backwards to statistics. He said, the mean looks like a very good estimator. Under what conditions is the mean a really good estimator? And it turns out when you have a normal distribution, because the mean minimizes, so the property of the mean among a set of values, if I give you a bunch of values and you give me the average of those values minimizes the sum of squared distances to all the values in that set. And that's what Gauss realized when he came up with normal distributions and all of this back in the day, right? We also might want to do event probability. Like Bayes isn't just about doing the probability. We might want to estimate, hey, how many people are going to have COVID next week? Who's going to win the World Series, right? What's the, who's going to win the election, I guess, if we're talking about something more on everybody's mind. So we can do a Bayesian event probability estimate. An event in statistics is just a set of parameters. Right? So that's all it means to be an event. You have some subset of the space of unknowns, right? And what's going to happen is the Bayesian event probability is just going to be the expectation of an indicator function over that set, right? So you're just basically saying this indicator function is going to be 1 if theta is a member of the set C, and it's going to be 0 otherwise, right? And if we average this, we get the probability of that event. So let's look at this example. This is actually the very first example that Laplace looked at in like the late 1700s. He had like 50 years of Paris birth records. He looked at it and said, gee, 51% of the births or so were boys. Can I be certain that there's a higher probability that a boy is born than a girl? So he set up an event probability that theta, he built a model, just a simple binomial model, where theta was the probability that a live birth would be a boy. And then he went and calculated from about 250,000 birth records in France. They kept very good records even in the 1700s, right? He worked out this probability from a very simple model that just said every birth is independent with probability theta being a boy, right? What Laplace derived was the answer to this was 1 minus 10 to the minus 42. In other words, 99 point, a whole lot of 9%. Right? And he concluded he was morally certain that more boys were born than girls. But this is how you set that problem up. This is an event, theta greater than 5. The event's technically just the open interval from 0.5 to 1. Right? So that's all event probabilities are in Bayes. Right? And the posterior predictive distribution, this is what we're going to do if we want to look at the probability of new items. I want to give you a probability distribution over things coming next. This is, for instance, what ChatGPT is doing. It's giving you posterior predictive distributions over what the next word is. Right? So y tilde is going to be new data that I haven't seen before. Y is going to be data that I've seen. And what I want to estimate is what's the probability or what's the density of that new data given that I've already observed some data. That's just going to be an expectation of its probability function there, the density function, right, averaged over the posterior. right? And if you look at this, there's two terms here. There's this term and this term, and the density of y tilde given theta is sampling uncertainty. That is, I may know the parameters exactly, but there's still some randomness involved in this process that we can't get rid of. No matter how much data we get, we're never going to reduce the sampling uncertainty. Right? That's just because I'm flipping coins, I'm engaged in something that's very random. But the p theta given y is estimation uncertainty. That's going to shrink as I get more and more data. I'm going to get more and more certain about that, and then all I'll be left with is sampling uncertainty. And of course, when we're doing this, we can condition everything on features or covariates or something. I've just dropped all of that from the notation. Right? And it turns out the way we normally compute this is with Monte Carlo methods. We do expectations via Monte Carlo. So if we want to compute the expectation of f of theta given y, this conditional expectation, and you'll notice that everything we talked about was in this form, right? Then all we do is we're calculating that integral. We're averaging the value of that function f over the posterior. That's going to be asymptotically exact as we take infinitely many samples, m. Just averages where these theta 1s through theta m are samples, are a sample from the posterior. These are draws from the posterior. They don't have to be independent draws, but they have to be identically distributed from the posterior, which is why MCMC can work as well as Monte Carlo methods. Right? So all we do is we get this very simple plug-in estimator. Sorry, there should have been an F over there as well. Right? That we take capital M draws and we just average from our posterior, and then we just average functions over them. So it could not be easier to calculate any of this stuff in Bayesian stats. It's one of the reasons it's so popular. Right? It's very easy to just compose functions, compose things you want to predict, compose predictions of event probabilities. Right? And the MCMC central limit theorem says that the standard error of our estimates, right, of this quantity, when we're doing this expectation, there's going to be some error in that because we've only collected finite amounts of data, and we've only collected finite amounts of samples, m. Right? So what this is going to say is the standard error, that is the error we expect to be making in estimating a parameter, is going to be the standard deviation of that, what we know about the standard deviation of that parameter given the data, divided by the effective sample size. That is, the m effective is like when I take m draws, they're acting like m effective independent draws, even if they're not necessarily independent. Right? All the details of this don't matter. I'm not even sure why I put this on the slide. Right? So I actually translated this talk from a talk about probabilistic programming languages. I already showed you an example for that, so I probably should have cut that slide. Now I want to go through and start talking about how are we going to do testing? How are we going to make sure, one, we have a reasonable model, two, that our model's actually fitting computationally, three, are we actually getting a reasonable fit to our data? Is our model doing a good job of capturing aspects of our data? And how does our model do predictively on new data? So I'm going to go through all of those things rather quickly, one at a time, right? And we're going to start with the prior. We're going to start with looking at the model and saying, hey, I had to put a prior down here, and I had to put a likelihood down here. These probably should be called model checks, right, to begin with, not prior predictive checks, because it's really, remember, you can't evaluate just the prior itself. This is evaluating the prior plus the likelihood. The idea of a prior predictive check is really simple. I just simulate data from the marginal distribution of the data, right? And I can do that by sampling some parameters, theta, from the prior, and then sampling some data from the sampling distribution. Right? That's going to give me a joint draw, theta sim, y sim from the joint distribution. I can just forget that theta sim, and then I get a y sim that's drawn from the marginal distribution of y. That is, if I get an AB that's drawn from the distribution, the joint distribution of A and B, I can just forget the B, and then I have an A that's drawn from the marginal distribution of A. Right? So this is very easy to generate data. Sample parameters from the prior, sample data from your sampling distribution. That's why we set these things up like a generative model like this. Then what you want to do is you want to compare the simulated data that you get to the actual data that you have, or what you know about what actual data looks like, and say, is this at all reasonable? When I do this, does this generate anything that looks even close to what reasonable data would be? Right, and this comes from a paper called Visualization in Bayesian Workflow that came out a few years ago. It's really about prior predictive checks, so often papers have the wrong name. Right, I think they really liked their plots, of which I'm going to show you one, which is why they called it that. And mainly it was because Jono was working on a visualization package called Posterior, so he started it thinking, I think they started this paper thinking it was going to be about visualization and then said, hey, hang on, this is a much more general thing. So this is some data. These 3 plots are, and you'll notice that the plot on the left and the middle have very different vertical axes here. This is for a particulate matter concentration pollution model, right? And the idea is that we're going to have some prior on the log of the concentration of particles, right? The thing is, they took the vague priors that people had been using in this domain before for other papers and said, hey, if we do simulated data, what happens? And this is what the simulated data looks like based on what the observed log particulate matter concentration is. And what happens is this concentration up here is like so out of control that this is equivalent to like being inside of concrete. Right, so this prior, and I think it's even worse. I think it may have been like a neutron star or something. I'm not very good at big magnitudes. It was something ridiculous where you're like, okay, this is just way out of control. And historically, people really liked very vague priors because they were what Andrew Gelman would call a cringing Bayesian, somebody who didn't want to be accused of putting their thumb on the scale. Right, so the idea is we want to be as prior-free as we can and have very vague priors or very non-informative priors. It turns out when you do that and you simulate data from vague priors, especially if you're in high dimensions, the data doesn't look anything like what you're doing. Contrast this with this idea of weakly informative priors. This is still not a good prior for this data, right? But what it does is it takes each of the parameters in the model and says it's roughly going to be on this scale when we're done. It's not going to be an order of magnitude bigger than this or an order of magnitude less. We roughly know what scale these parameters are on. We've been doing this work for decades. We're not ignorant when we start modeling. And then this plot on the right just puts both of these on the same scale. So that just combines these 2 plots. You'll see this data from the weakly informative prior is fairly reasonable. It's giving you still like it would kill everybody on the planet level of particulate concentration to we're in perfectly clean air and space concentration, but that's better than being inside of a neutron star, right? The problem with prior predictive checks is if you want the prior predictive checks to look really good, they should essentially be your posterior, right? We don't want to go that far in terms of putting a prior on. So there isn't really good guidance here. I'll answer the question that you may have had. We don't really have good guidance on when to stop doing prior predictive checks and when enough is enough.
This is a scatter plot sampled from the joint distribution. Theta is across the x-axis and y is the vertical axis. Is that right?
Yeah.
Okay.
Yeah.
All right.
Yeah. Yeah. Y is the concentration, I think.
That's what you.
Yeah. Now
you're
that I
trying
write
to
this up, I
predict?
think I need to go back to the paper and see what these axes actually mean.
Well, I know what particulate at PM 2.5
Yes.
is.
Yeah,
I know what
but
that
somehow
means,
I thought that was the
but
y-axis.
you're actually predicting whether people will die. It's like this is number of heart attacks per year or something. Is it in vertical axis?
Maybe I can't remember.
There are a whole bunch of, I don't know why it's 1 to 5.
Anyway, I don't think it matters. I don't think the details of this don't matter. Do you have a question, Alex?
I was going to ask if the main guidance here is, I guess, 2 things. One is like visualize, plot the data, and 2 is check the order of magnitude.
Yes.
I can
That's
kind of like
that's the takeaway message. yes.
imagine some like maybe cases where I have high dimensional data. It's like difficult to visualize and maybe
Yes.
difficult to even check the order of magnitude. Are
Yeah.
there other
Well,
things or?
We're gonna talk about how to do that in a second. Yeah. There are ways to look at marginals and do that essentially. Right. Generally, these things put things back on the data space. So even if you have a super high dimensional model, we typically simulate back in the data space. Right. Now I'm going to give you something crunchy. This is some math that'll actually work. Right. So this is what we call simulation-based calibration, or what Andrew's now calling simulation-based calibration checking. because we're not actually calibrating with this. We're just testing whether things are calibrated, which is good. We kind of misnamed this at the beginning, right? And what this is doing is this is evaluating whether our inference algorithm works, right? So I've thrown down some new inference algorithm. We're doing simulation-based inference. I'm doing Monte Carlo methods. I've built a diffusion model. And I have the question, is this algorithm, if I simulate data that I know the answer to, is this algorithm actually going to recover the right answer? Right? Because we know the right answer when we simulate data. At least we know we should have good coverage, right, probabilistically. Right? So it's called simulation-based calibration because, again, what we're going to do is we're going to simulate a bunch of data sets, and then we're going to lean on some probability to derive some things that should hold, and we can turn those into statistical tests. So what I'm going to do, and I'm going to do this repeatedly, right? These things, these sub-bullet points here under the first big bullet, we're going to repeat this process 100 times, 1,000 times, whatever our compute budget will afford, and that can be a problem. So we're going to draw simulated data from the prior, and then we're going to draw simulated parameters from the prior, and then simulated data from the sampling distribution given the prior. Right? So now what we have is we have a joint draw, y sim, theta sim, from the joint distribution, just by construction. Right? Now what we're going to do is we're going to take the algorithm that we're testing, and the algorithm's going to give us a bunch of posterior draws. Right? So it's going to give us theta 1 through theta m drawn from this algorithm. If the algorithm is correct, if those draws actually are draws from the posterior, then y sim in each of those theta m's, each of the little theta m's, every element of this list is also a draw from the joint distribution. Now we're getting somewhere, right? We have a draw over here from the joint distribution, and then we have a whole bunch of draws over here from the joint distribution. What do we do to test that this is working? Well, it turns out that theta sim and the theta m should be identically distributed. They're both marginal draws from the prior, if everything's working correctly, right? So given conditioned on the data y sim, right? So what we can do is we can test for each dimension d of theta, we can test that theta d sim has a uniform distribution in terms of its rank through the theta m's. Since we assume these to be identically distributed, the theta sim and all of these, then this should show up anywhere in that sequence with equally likely probability when I repeat this procedure a bunch of times. Right? So that's what we're going to do. Repeat the procedure a bunch of times, perform a statistical test of uniformity here. Lots of ways to do this. In the original Samantha Cook paper, she did this by inverse CDF transforming to a normal and then doing a test of normality. You can knock yourself out here. In terms of how you do this. Some of the later papers have suggested you just eyeball some scatter plots like this. Right? So this is what's going to happen. I'm going to plot the ranks here, right, of what I actually get. Now what I'm doing is I'm plotting the rank of this among this over multiple tries. Right? And that should have a uniform distribution if everything's working right. Right? But what's going to happen if it doesn't have a uniform distribution, we can actually look at the shape of the distribution here and learn where our algorithm's going wrong. Right? Our algorithm might either be producing over-dispersed things with too much noise, things with too little noise, or it may be biased. It may be producing answers that are way off to one side of where they should be. You want to know this about your algorithm before you apply it and trust its results. Right? If you're using something like MCMC methods and they're actually working, all of this will work just fine. If you're using something like an approximate method, like variational inference, we know this will fail if you make this test big enough. So what to do with this for approximate algorithms, I'm not quite sure. But for exact algorithms, this is a good test. Right? So we do use this on algorithm tests. Right? So we've looked at how do we check our prior and that our model makes sense at least a little bit. We generate data, see if it looks like the real data we get. We're going to do something similar now to try to evaluate whether the model's well specified and actually captures features of the data we're modeling. Right? So I've given you some data y, and I fit this model. I have a posterior. And you want to know, is that posterior good? right? What we're going to do, if you know things like chi-squared goodness of fit tests for regressions, this is the Bayesian equivalent of this. It's something called a posterior predictive check. I think it's something Don Rubin introduced in the 70s or early 80s. So you want to check whether the models actually fit the data well. So what are we going to do? Well, we've only got a few tricks in our books. We're simple statisticians here, right? We're going to simulate some more data, right? I've got my posterior, p theta given y. I'm going to simulate some data from the posterior. But now I'm going to do this the other way around. Now what I'm going to do is I'm going to take this draw from the posterior, theta m, and I'm going to simulate some new data. So the idea this time is I've actually fit the model. I've got some posterior draws for plausible parameter values. I want to make sure if I generate data from those plausible parameter values from my posterior, I get something that actually looks like my data. So what do? Well, I compare statistics. A statistic is just some function on a random variable, right? It's just some function. Typically, we use things like mean, max, standard deviation, quantile functions, ranks, things like that are easy to compute, and we can interpret them. But this can be any old function you come up with, right? And what we're going to do is we're going to look at the statistics we get on the actual data set we have and on the simulated data sets where we've simulated from posterior draws, right? And we can do this once we do this, we can actually calculate the Bayesian equivalent of p-values here, and that we can look at the probability that sy, the statistic on our data, is less than our simulated data, right? The randomness comes in through this simulation and the probability. These are just constants here, right? So we can look at the probability, and this is equivalently a two-sided test, basically, that I created here, right? You can actually, this is an event probability. We can look at what's the probability that the statistic is less than that statistic, right? So let's see what this looks like in practice. This is from a case study that I wrote on repeated binary trials, which, if you want to learn about Bayesian hierarchical models, I can still recommend. It's for baseball, so it's very, very applicable now. This is replicated data for posterior p-values. This is on, I can't even remember this is max, min. I think this is number of hits for the data that's actually happening. We're actually looking at something like 50 at-bats at the beginning of the 1970 baseball season. This data was drawn from a super influential paper by Efron and Morris in 1975, where they introduced the idea of empirical Bayes and the idea of doing shrinkage of your estimators. It's a really cool paper, and you'll see just what a struggle statistics was in the mid-70s. They had to normally approximate everything. They could barely do anything computationally. Now it's like easy to do all this stuff they struggled with back then, and now we're struggling with a different set of things because we're trying to do harder stuff, right? But anyway, the horizontal bands here are faceted for 4 different models, right? Based on whether I'm doing partial pooling, whether I'm doing partial pooling on the log odd scale, whether I'm doing complete pooling or no pooling. The idea of pooling is, do I treat all the players as similar to each other and pull all their estimates close together? The no pooling model means I treat every player as if they're completely independent of the other players. The complete pooling model says I assume every player has exactly the same ability, right? We've only got a small amount of data here. It's about 30 players, about 50 at-bats. So we've only got on the order of like 1,500 binary trials here. It's really weak data. So the data we have in this experiment is only really good enough to reject the no pooling model. The idea that says, well, each of these players is completely independent. They're not drawn from any population distribution. The one model we reject is the one you would get from a simple maximum likelihood estimate. Right? So what this is saying is you really want to do the pooling, and that was Efron and Morris's point in their original paper. Even if you're a frequentist, you don't want to take 50 data points and form a maximum likelihood estimate. Shrinking to population means will really help. In fact, it's very hard. You generally need more than a couple seasons of data to really confidently conclude that baseball players have different abilities. Right? It's actually a difficult, challenging problem. Right? And what's drawn here, the vertical line, is the value on the data. The histogram is the value on the repeated trials, right? So those are the simulated data. The statistic on the simulated data, and I'm looking at min, max, mean, standard deviation, right? And you can see that the no pooling one is way off, right here. If you had more data, you'd pretty much be able to reject everything other than the partial pooling models. Right? I've done this. So, okay, so that's checking. Does the model that we have recover features of our data? Like, does it get the variance of our data? Does it get the location and the mean of our data? Does it get the extremes of our data? Right? And if all these things look good, then we're pretty confident that our model's actually capturing aspects of our data generating process. Right? But so far, this is all in sample. Right? So we're being typical statisticians. We're doing data analysis for a fixed data set. What we really care about is cross-validation. What we want to know is the model going to be predictive for new data? And I'm going back to this notation I introduced earlier where we've got y tilde is new data, y is observed data that we're going to train on. So in the machine learning world, people call this the train-test split or the folds for cross-validation. We're going to fit the model on the training set, that is y, and then we're going to evaluate the predictive log density on the test set. Right, so, which is this, right? We're trying to evaluate, we've got some test set y, and we want to know how good are we doing at predicting the elements in our test set, right? What this was for Efron and Morris is this was the rest of the baseball season for these players, right? So we looked at their first 50 trials, and then we took another 450, 500 trials, and we looked at that as the new data, y tilde, and we're trying to build a model that says, can I observe how a player does in the first 50 at-bats of a season, you know, the first couple of weeks, and predict how well they're going to do for the next couple of months, right? And this is how we do that. We do cross-validation, and all we're doing is we're trying to figure out what the probability is of the new data, right? This is what's known as the expected log probability density, or ELPD. Right? I didn't write that notation down, but if you see that, and of course, we have to work on the log scale. We want the log of this. We can't just multiply all these things and work on the natural scale, or we get all kinds of numerical issues. So we have to work over in the log sum x world. But otherwise, this is all we do. Right? The neat thing about this is you'll notice this may look very unusual. If you're used to coming from machine learning, this does not look like cross-validation in that world. Cross-validation in the machine learning world is I've got a bunch of images, they're labeled with dogs and cats. Cross-validation is how many images did I classify correctly in the held out data. That's not what we're doing here, right? What we're doing here is showing you how you can do cross-validation like this just on the data. Right? We don't need any hand-labeled things here. You'll notice this doesn't rely on anything being hand-labeled. There's no gold standard. All we're doing is dividing our data up and saying if we build a model on some of our data, does that predict the rest of our data? Right? Now, it could be that this data is labels for things like categories of dogs and cats, but it doesn't have to be. This is a general method that you can literally apply to any problem you have. Difficulties that come in, though, is when these are not IID, right? Then it becomes difficult. If you have a time series model where you're observing a bunch of stuff and then you're trying to predict something that happens later, you can't just chop that data up and do naive cross-validation. If you go into something like scikit-learn, it has a really good API for doing cross-validation in terms of grouped data and time series data and things like that. They really thought that through better than anything else I've seen published. We have a bunch of papers around this, around Stan and how to do this, but really scikit-learn got it right. Finally, last point, I think this is the last point I want to make, sensitivity analysis. We want to evaluate, one of the things we want to do is we've laid down some priors, and we can do prior predictive tests, but that's, in some ways, we don't really know how to calibrate those. We don't really know how to read the answers coming out of those very well. What we can do is something called sensitivity analysis, and this is a notion that came out of the applied math world, where you'd do something like you would fit a differential equation, you'd use a differential equation solver, and you'd want to say how sensitive is my answer to my initial conditions, or something like that, right? So they do that differentially, right, where we can do something like, if we're computing some expectation and it depends on something, some amount of data, some constants, something, this is maybe a scale parameter and a prior, I can calculate a derivative through here. That's hard, right? It's not impossible, and now with tools like JAX and things like that, it makes this kind of thing a lot easier than it used to be a few years ago. But essentially, a simpler way to do that is to just do a discrete grid. Say, I chose a prior. Let's look at some priors that are very close to that prior and see if changing my prior to that changes my downstream inferences. Right? So here's a plot from a paper I wrote with Andrew Gelman. And interestingly, this is my one contribution to this. This was the easiest paper I ever wrote. It's like 2020 COVID paper. They were accepting anything, especially if people like Andrew were involved. And Andrew's just like, hey, I don't have time to do a sensitivity analysis. Can you do the sensitivity analysis for this? And we'll go publish it. So, and that was pretty much that and making the code actually reproducible. Right? So what this is this is a COVID example. The vertical axis is the prevalence estimate, the estimate of how many people have COVID. We were reanalyzing this bonkers Santa Clara study that some nutty professors at Stanford did. What we've got is two hyperpriors. One's represented by the facets, and that's the prior on sensitivity. That is, how accurate is the test if the person actually has COVID. And this is the specificity hyperprior, which is how accurate is the test when the person does not have COVID, right? So we have sensitivity and specificity. From those, we can work out prevalence of the tests. If we know the profile of our tests, we know the test results, we can back derive prevalence out of it, which is what we did in this paper. It's a sort of a clever use of hierarchical models. I was frankly surprised this got accepted. This is the kind of thing you might assign as homework in a Bayesian data analysis class. I mean, we did it right, but this would have been an A on the homework, but it really felt like homework. It was applied to COVID at the right time, right? So what you see here is that really our estimates don't vary much at all. And this is the interval here is the 90% central interval. Right? But if you look at our point estimate for what the prevalence is, that doesn't change much at all depending on what the priors are. So pretty much no matter what we make the prior, and this is over a broad range of priors here that we're using. So over a broad realistic range, our conclusions don't change that much, except in terms of how certain and uncertain we are of the results.
Can you also, if you don't make the sensitivity and specificity hyperparameters, but you just treat them as unknowns as well and put in uninformative priors on them.
That's what we're doing.
Can you learn how accurate the tests are and stuff?
That's exactly
well?
that was the point of this paper.
Okay.
That's exactly what we're doing, trying to estimate what the sensitivity and specificity of the tests are so that we can infer this. But then we have hyperpriors over that. So those are unknown, so we put priors on those as well. Right. So the thing is here, the one thing I didn't mention is this is over
already, they're already hyperparameters.
The reason this probably didn't make sense is I didn't tell you the critical thing here. This is over 20 or 30 different testing sites. And we're modeling each testing site as having different sensitivity and specificity.
So you are learning all of those.
So we're learning all of them. Yeah. And the hyperpriors are the prior on the population model that says the population of testing sites are drawn from this particular kind of distribution. Okay, so I have a few slides here, but I think in the interest of time, I'm just going to take this as given. When we're doing workflow, there's a whole lot of other stuff that goes on that we might want to do, right? A lot of this comes down to, we've actually got 5 or 6 models in our pocket we want to try. How do we keep track of them? How do we name them? How do we put them in our version control system so we don't get super confused? So, I mean, this is what our directories wind up looking like. Right, we have this is something Mitzi and I were working on with the UK Health Security Agency, and we were working on all these spatiotemporal models of COVID evolution, and plus there's multiple ones of these, right? How do you work in distributed teams, right? You may have privacy issues, you may have to wind up deploying this all in production, right? And I'm sure we're missing a bunch of stuff here, but I think I'll stop there at least to leave time for a few questions. There's the workflow paper here on arXiv. I forgot to put the number on, but if you just type Bayesian workflow arXiv, you'll find it. There's a GitHub repo where a book-length version of this paper is being developed. The paper was already 60 pages long with 15 authors. The book's even sort of more of a mess. But it's open access, and you can go read it. They're trying to bring it all into I decided it would be too crazy to work on the book because there were too many authors and too much stuff flying around. So, questions?
So we have the issue in astrophysics, to give a specific example, where we're trying to fit a model to a spectrum of galaxies, and we have the prior distribution on certain parameters. We find that it is important, but the actual fitting is so expensive that typically what we do is we just pick sort of maybe 3 like reasonable priors, and we can't sort of do something as rigorous as what you're talking about here, where you have some parameter controlling the prior. One approach people are doing now is to try to develop emulators to accelerate the actual model fitting, which makes sense.
that's what I was calling amortized inference.
Okay, so is that basically the most natural?
It is, but then you have to test that works.
Yeah.
Right. Yes. Yeah.
Is there any other?
No. The problem is once the compute gets big, and I mean that level, but then we're looking at like foundation models. Like no one's doing anything like this. They're fitting it once and they're happy they can get the optimization to roughly converge. Right? No one's spending $10 million and fitting this model again. Right? So at that point, then at extreme scale, you have to start making compromises here. And I think that's the best you can do. It's very similar to the advice we got earlier of try a finer step size in your model and see if the results change. Right? So it's the same basic idea coming throughout all of this stuff.
All right, I'll throw in
We
one.
could duck out and try to get back on schedule.
So you, in 2 different places in the talk, you like in prior predictive check and posterior. Well, in the prior predictive check, you sort of said, look, we've got one-dimensional samples from we've got samples from a one-dimensional distribution, from 2 different sources, and we want to check that they are coming from the same distribution. Yeah. Now, immediately, to my mind, I think of Kolmogorov-Smirnov. I mean, we talked about this.
Yeah.
But you showed this like rank thing, and then
later
on,
all those tests are just going to get rejected, and then it's a matter of do you want to work on the scale of p-values to try to understand what's going on.
And then sort of related, you then showed like later on you've got actual data that you want to check. 2 distributions of data look like in a high dimensional setting. Right. What are the is there a sort of toolkit for that you could just? It seems like that has to get reinvented either by making a new set of statistics, especially for the high dimensional
We're
stuff.
typically just looking at the marginals, but yes,
right.
there are. Let's just say the theoreticians are all over that problem.
I like you're really good at black boxing things, and we all need to be to make like tools.
Yeah.
Is that a separate black box tool? Compare that this stuff, that these samples come from the same distribution as these samples, either in 1D or many D. Yeah. Is that a black boxable thing?
That is something people are certainly working on doing. I thought you were going the other way and looking at like higher dimensional convergence and things like that and tests. So you can extend those, but it gets harder. It gets a lot harder. I think Charles knows more about this than me. It looks like he's about to jump in with an answer.
More of a thought than an answer. Which was that, so my initial reaction is that, so there are a lot of places where we can do these tests and where we're comparing, samples from different sources, and we're hoping that they're the same. And I think there are cases where we really want them to be exactly the same, and so this hypothesis testing regime makes a lot of sense. There's a null that does make sense. And then there are other cases where, either it's asymptotically, they will come from the same distribution, but since we're in a non-asymptotic, we know that the null is false. We already know the null is false, and now it's just a matter of, if we resolve the test well enough, we're always going to reject. Right. It will always fail, and the saving grace is that somehow we're not doing the hypothesis testing well enough to detect. So that's not satisfactory, and that to me is a case where we kind of want to shift to a tolerance framework or decision framework. But then I think that in a similar vein, so when we're talking about approximate inference, really the question is not, are we getting it right? We know we're not getting it exactly right, but what error do we tolerate? And again, this hypothesis testing framework is too rigid for that.
Yeah.
On the other hand, the test statistics that hypothesis testing is based on are not too rigid for those tolerance frameworks.
Yeah, that's what I was trying to say when I said the tests are going to fail. Do you want to work on the scale of p-values to like compare things, which sometimes, yeah, it's useful.